fantastic week last week, and already the first couple of days here likewise. So following the instructions from Glass, I'm also going to give a slight overviewish part, but I also want to convey a message. The message is in my title, and I'm going to try to convince you that from a certain point of view, with some assumptions, you should really think about strong translational symmetry breaking as an important aspect of the physics that you see in cuprate strange metals. So this is part of this larger story of explaining sort of unconventional metallic type behavior with virtual black holes. So before that, let's try to understand what a strange metal is. We already had Peter's talk earlier this week, who explained some aspects, but let's review some of it at least. So the strange metal in particular that we're thinking about is this phase in the phase diagram of high temperature copper oxides, right? So it's not the superconducting phase, not the pseudogap phase, it's this phase, roughly speaking, when you're at optimal doping above the superconducting transition temperature. And that's the part of the phase diagram where the response is very anomalous or strange, right? And what is strange about this response? We've already had several times this week mentioned that there is a linear linear temperature resistance in this middle, and the real important part is that this linear and T resistance continues as far down in temperature as we can see. Very high temperatures, also in ordinary metals, you have a linear and T resistivity due to phonon exchange, but the point is that this continues down all the way to the lowest temperatures. Whereas in an ordinary metal, if you go down to the lowest temperatures, below the Debye temperature, you expect a resistivity which scales as T squared. So this is one anomalous aspect. Then if you look at the optical conductivity, so you drive the frequency-dependent electric field, then in the mid-infrared range, you see something that looks like a power law scaling behavior, which is also very different from ordinary metals. In ordinary metals, you should see sort of three regimes. There's a very low frequency regime where you have a Drude peak. I will also come back to this later, but this essentially is sort of the collective motion that experiences resistance and decays. This is the ordinary transport. Then there's a regime where basically not much happens, and then at some moment you excite the system with high enough frequency that you have interband transitions in your metallic system. The third very well-known aspect is, and this will come back in this talk as well, is the Hall angle versus DC resistivity scaling. If you take the ratio of the Hall conductivity to the longitudinal conductivity, this is observed to scale as 1 over T squared. If you have an ordinary metal governed by a single relaxation rate, this power of T should be the same power of T here. So that's in ordinary metals, that's the same, but in a strange metal, this is different. So here the squared has dropped off, unfortunately, but in an ordinary metal, these are the same. That's the curious part. So it's not the T squared scaling, that's the same as an ordinary metal, but it's different from the DC. And then there are other aspects, no plasmon, that was the part of Peter Abramondes' talk in this story. And then there are also more subtle signatures. For instance, something that was, amongst others, pointed out by Blaise Goutureau is that if you look in the data, that if you look at the optical conductivity, but at high temperatures, the Drude peak seems to slightly move off from zero frequency. Okay, and then there's a whole aspect that I haven't mentioned yet, except for the Hall conductivity, about magnetotransport. Also, if you look at the longitudinal magneto-resistance, right, there's also very anomalous type behavior, which I will come back to. But I want to emphasize that if you look at this review about strange metals, there are 3 parts that are related to non-magneto response, and there are 4 parts related to magneto response. In the view of these physicists, right, the magnetotransport is really an essential part of the anomalous strange metal behavior. So that's what we're going to focus on. Now, there are many attempts to explain it, right? And I think there's a consensus now that one aspect of the resolution is the fact that the physics of the strange metal is driven by a quantum critical point. So it's by a phase transition at 0 temperature. And especially if this is a second order phase transition, then something very special happens. At a second order phase transition, you have a divergent correlation length, you have universality and scaling. And the interesting part is that when you now introduce temperature, so you reintroduce a scale, you don't lose that particular scaling behavior, right? In fact, what you get is you get a finite temperature scaling theory, or a quantum critical fan, as it's called in experiment. And this whole region is then controlled by the universal physics at this critical point. And that's and often this universal physics has very interesting behavior because of its universality and because of its power law behavior, because there's no intrinsic scale. And that anomalous type behavior is thought to underlie. So this, some way or other, right? Peter introduced on Tuesday this phenomenological explanation of what happens in a cuprate strange metal. Some way or other, there should be some underlying quantum critical theory that gives you MFL type phenomenology out of its story. So that's what we're going to try to do. Now, because this was such a hard problem, people threw many interesting approaches. So one approach that we were part of is to try to understand these anomalous, sort of these strange non-trivial fixed points, which are often interacting. So you cannot approach them by perturbation theory, by using a inherently strongly coupled approach. And then some strongly coupled theories you can, oddly enough, describe in terms of gravitational physics in one-dimensional higher. And we said, let's try to use this tool to try to understand perhaps something like a strange metal rolls out. And if you do that, you have some dual gravitational description of a strongly interacting quantum field theory, and you try to find some non-trivial fixed point in this theory. And if you want to study this at finite temperature and finite density, then the gravitational theory generically should have a black hole in its interior. So this is where the black hole part of the story comes from. So we're going to study some charged black hole in ADS, so that's the computation we're going to do. But I want to emphasize throughout that this is going to be a tool, right? We're going to get some results out, and rather than trying to sort of understand these results in gravitational language, which is cool and interesting, we also want to understand it in terms of sort of the more conventional physics language. So just having a gravitational computation that spits out something that looks promising, right? That's the first step. The second step is then to understand it without having to refer to this gravitational picture, right? The point, of course, that this gravitational tool is very powerful and it's quantitatively exact. There's an exact map, right, between the gravity side and whatever you are computing in the strongly correlated field theory. So you ask me what to compute, and this machinery will compute it for you. So let's try to apply this to the strange metal phase, or let's try to see if something like a strange metal can come out of this approach. Now, one thing I want to emphasize that the starting point here always is already, right, AES CFT. The CFT stands for conformal field theory, and the starting point already is a critical theory that is strongly acting in high dimensions. But this is some relativistic zero temperature, zero chemical potential CFT that clearly has no relevance to what you see in condensed matter. So you have to do something to the system to try to get to a strange metal. So what we're going to do is we're going to deform this theory, trigger an RG flow, and then hope and pray that it lands on something that we haven't seen before, right? It also means that there should be some way to deform it that you'll land on things that you do know, right? So indeed, there are ways, it took some time in the literature, but you can deform this conformal theory and get an ordinary, well, a sort of holographic version, but in essence, an ordinary superconductor out of it, or an ordinary sort of Landau Fermi liquid type out of it. But the interesting part, and that's sort of the part of the excitement, that already in the very early days, you found some very anomalous responses. So there are some infrared fixed point of this theory that doesn't respond in the way that we understand it from conventional perturbative, weakly coupled Fermi liquid type approaches, right? And the essence of this is some funny near horizon gravitational SYK type physics in this story.
Can I ask a pedestrian question?
Yeah.
So I've always wondered, so the CFT is always critical. It's a scaling variant.
The UV theory, yeah, yes.
But you can, but generically that doesn't project onto the quantum field theory that you're trying to describe.
Yes, exactly.
And if you don't do anything special, does the quantum field theory end up being scale invariant too? And then
no, because you introduce a scale, right? You trigger an RG flow.
So you have to throw some stuff in, some disorder or
something like that, disorder, or often, right? What we do is you introduce some particular operator, often a scalar operator. This drives some RG flow, and you try to force it to flow to some new infrared.
Okay, and that doesn't break the whole theory or anything when you do that.
There are sometimes cases where this breaks the theory, so you have to be careful that you stay gravitationally under control. Okay. But there are situations where it drives it to a system where you're outside of the regime of your classical gravity computation. Then you would have to introduce quantum. These are difficult. You try to avoid that, of course, not because you don't want to, but you lose control. Okay. So one classic way to deform it is just to add a scalar field with a potential, right? That's where it rolls down to potential, and then there's a very generic story that you end up with indeed a set of very novel critical points that generically have this Lifshitz scaling type behavior. So here you already see that the relativistic scaling that you had in the UV has changed in the IR to some novel scaling with an emergent dynamical critical exponent Z that tells you how time scales with respect to space, right? Also mentioned what's called local quantum criticality, right? In essence, this means that space sort of decouples and becomes sort of an extra quantum number in the game. And many of the response functions are therefore only functions of frequency, and the momentum does not play a large role. Now, where does SYK fit in the story? Because that's sort of interesting. The SYK actually illustrates this philosophy in a very clean way. SYK is just a model of interacting fermions on a dot. But if you go to the UV of this model, it is literally free fermions with a weak interaction, just like you learn in your first year graduate condensed matter course. So the UV of this theory is a nearly free theory. It's not critical. Right? Looks very, very different. You can solve it, right, with a perturbation theory approach. Of course, this is not where the interesting physics lies. Right? The interesting physics lies in that this is actually a solvable model that also flows to a non-trivial IR fixed point that's strongly interacting. And the interesting part about, and that's where the K part comes in, but also Subir Sajdev already realized this very early on, that this is actually the same fixed point that was found independently by doing these deformations in holography. Right? So there's a regime where SYK will give you completely different answers from what you see in holography. That's sort of at intermediate or high scales, but there's also a regime where these answers are the same. And therefore, I can use SYK type models or holography type models to study this type of fixed point. We're going to use this, but other people have used this. And I will therefore jump a little bit for motivational reasons back and forth, and you will see why. Okay? The reason why is one of this is that particular from the SYK side, SYK has done a lot of things, but there's also been this idea of trying to apply it to the cuprate strange metals. And there's a version of this SYK model called the Yukawa SYK model. Here's the Yukawa. That in a particular version of this has now shown many things that you observe in the strange metal. And I could really think, you can think of this as a partial breakthrough, because in one model, they have a linear T resistivity, a T log T specific heat, this marginal Fermi liquid spectral function, and particularly, this was very hard to get, but you see already this sort of power law regime in the optical conductivity in the mid-IR range. One of the things that comes out of this paper is that that's not actually strictly a power law. It just looks to your eye like a power law, and you can understand mathematically why this is so. So this isn't a power law, but to your eye, if you put it on a log scale, it looks like this. All right, and so this is really in one model, you have all of this, but by the same story, right? It is the same model as one of these holographic type models. So we're going to use the holographic approach, but there should be an exact holographic model that also reproduces all of this. And there are various holographic models that can already reproduce 1 or 2 of these. The exact one that produces all 5 of this is still in the works, but I'm sure it will come shortly.
Can I ask another question?
Yes.
Can you remind us how YSYK is different from just SYK?
Okay, so there's a very easy way to understand it. Standard SYK has a 4 fermion interaction, right? With a disordered coupling.
Yeah.
If I have a normal 4 Fermi interaction, what I would do is do a Hubbard-Stotanovich transformation with a scalar, right? And then a scalar fermion-fermion interaction. That is the Yukawa SYK model. If you make those couplings disordered rather than discoupling disordered.
Okay.
So it's essentially the Hubbard to TJ model type transition.
Yeah.
That kind
But
of.
of course, that Hubbard-Stotanovich is algebraically exact. But if you now make the boson dynamical, right, that's when you get the Yukawa version.
Wait, so wouldn't regular SYK have kind of no spatial dimension? It's like a dot.
That's correct. So this version is a 2-dimensional version where they have a
You put a
lattice
on every.
That's right. That's correct. But the lattice is just an ordinary, simple, single fermion hopping from side to side. For instance, there was a talk here yesterday about a transport in SYK model that had a Q-body hopping. It's a different way of building a higher dimension SYK model. Okay, so
correct me if I'm wrong, but there's no holographic model that we know of that gives the T log T specific heat, right?
I would have to think. I cannot name one on the spot if you would ask me.
I would say that's one of the outstanding challenges.
Good. Yeah.
So that gives no the heat capacity, not T log T. I would think you just get that by Kremers-Kornig. From if it's like proportional to a mass.
So in these holographic models, you can get a variety of behaviors, but that I know, there is not a model that gives you a heat capacity that goes like T log T.
I would think anytime you have a linear and T self-energy, something like a self-energy, you get T log T to its corresponding.
But in holography, we don't have self-energies because we don't have quasi particles. So that line of reasoning doesn't really apply.
SYK gives you T log T.
I know.
So, okay.
Yes.
Oh,
There's a holography.
No, it's a
little wrinkle.
This duality between SYK and ADS2 type holographic systems, there are similarities, but I would say that there are also differences.
Yeah.
Sorry, but does that then mean they don't flow to the same endpoint here? Or, I mean, if you get in the SYK model, you get it, then shouldn't you?
The statement is that they have the same infrared effective theory in the form of this Schwarzian. The conclusion I would draw from this is that the Schwarzian doesn't govern everything.
Yes, that is yeah. So another way of saying it is that in most critical theories that we know, there's a unique set of critical exponents that is related to it. These theories with you can either say a Schwarzian or ADS2 symmetry, they're just saying the symmetry is not enough to tell you the set of critical exponents in the theory. You need more information, right? And that's the other way of saying that the Schwarzian the symmetry doesn't fix everything. Okay. So now, one of the lessons that sort of we learned from this holographic type approach to these quantum critical systems, but it's a lesson that was already independently known in quantum criticality, is that transport in these systems, you should think of transport more in a hydrodynamical sense than in a Boltzmann sense, not as something that creates from quasi-particles, but precisely that's something that's an emergent collective phenomenon, right? And one of the reasons is already sort of from the quantum critical point of view, it was already realized very, very early that when you look at these theories at finite temperature, right, I told you that you inherit all the scaling behavior. Well, this is not, this is true, but as you probe the system, sort of start probing in the system at the temperature scale, it does know about the temperature scale in the following way, that what was pure scaling behavior, if you look at scales much, much larger than the temperature, where sort of the difference between being at finite temperature or at the zero temperature state is sort of a correction on the system, and so you expect pure scaling behavior. The moment you probe it at scales beyond that are lower than the temperature, and you should really know that you're in a finite temperature system, you very quickly enter into a hydrodynamic regime where the conserved quantities in the system control everything, and there's not much else. Because there's no features in the system, this essentially is then sort of a featureless hydrodynamics that is left over in the system. So one of the aspects of this also is that inherently is that you get a very early onset of hydrodynamics, sometimes earlier than you might think in these stories. Okay, and sort of the intuitive picture of what this is going on, and this was already illustrated in Andy Lucas's review last week about electron hydrodynamics, is that in ordinary electronic systems, right, the mean free path of electrons is actually very, very large. A Fermi surface is a free infrared fixed point, right? So the perturbations are very weak when you're at low energies, and electrons can travel very, very far, and particularly can travel much further than generic lattice length or the disorder scale in the system. These holographic type systems, they're inherently strongly coupled, right? Or quantum critical theories are systems with no scale. So in a certain way, the mean free path is sort of approximately zero. So these systems collectivize on very, very short scales, and particularly they collectivize at scales shorter than sort of a lattice scale or disorder scale, which is other relevant scales that you think of in matter physics. And therefore, sort of the phenomena that you get is much quicker, sort of this hydrodynamic type phenomena rather than a ballistic type phenomena that you would expect in very simple Fermi liquid theories. So this is one of the things that comes out. And this is the quantum critical side of the story, and if on the gravity side of the story, it's in essence the same thing. Also, the gravitational theory is based on the concept of conserved quantities. Here, the standard quantity is energy, whose dual is the gravitational dynamics. And there's a beautiful mathematical map how it even has its own name, the fluid gravity correspondence, how in these ADS CFT models, you immediately get hydrodynamics out of it that governs your response. And there's no sort of hierarchy of scales. You just get hydrodynamics right away at low frequencies or frequencies beyond the temperature. And sort of one of the ways you can, this helps you is that it makes it very easy to compute finite temperature real frequency response functions in these systems compared to standard methods in quantum field theory. And it also has yielded us sort of the bigger picture of theoretical physics some interesting results. Right, so if you do second order gradient terms in relativistic CFT, which are very important, for instance, for heavy ion collisions that people study, these were actually by one of these computations in ADS CFT correctly identified for the first time. Of course, after the fact, people realized that they had simply missed something, but the ease of doing this yielded the first answer in AFT. And another very interesting aspect is sort of people also realize that you can have these funny parity-odd type hydrodynamics, which is also something that sort of rolled out of people thinking about ADS CFT. It is, again, something you could have done without ADS CFT, but the ease of which you do this is something here. And let me illustrate sort of in 2 seconds the ease of what's going on in ADS CFT. And it's a little bit of a sketchy dimensional analysis type problem, but it tells you what's going on. So let's compute the shear viscosity in one of these systems. Now I'm going to take the relativistic system at zero density, right? It's given by a Kubo formula, and right. So this is a finite temperature Green's function that you have to compute. Normally, you would have to do this on a Schwinger-Keldysh contour. It's a lot of work, right? But if you use ADS CFT, you can realize that the imaginary part of this stress energy tensor, the dual of the stress energy tensor is a graviton. For the shear mode, you need a transversal graviton. That is very easy. But the imaginary part of a graviton-gravity correlation is, by the inverse of the optical theorem, is just a cross-section. So this is just some cross-section of a graviton impinging on a black hole. And then there's a general story that you know that if you have very, very low frequencies, which you have to take for the viscosity, the cross-section of anything is its geometric size. So the cross-section is about proportional to A, and then you know that A is equal to the entropy of a black hole. So in sort of 3 lines, if I get that the viscosity in units of the entropy is some number, right? This is sort of an illustration of the ease of ADS CFT and how hydrodynamics falls out. Now, hydrodynamics is also very important in matter physics, right? The Drude model is in essence sort of a simplified version of hydrodynamics. And I'm quoting it here because this will play a role in the rest of my talk. And also one of the things that, again, this was known without ADS CFT, but was re-highlighted by ASD, because the theory we start with is relativistic, you get a slightly different formulation of the standard electrical conductivity, the thermoelectric cross conductivity, and the thermal conductivity in terms of these relativistic quantities. And then there's an anomalous sector as well, which you normally don't see in non-relativistic or particularly Galilean systems. Galilean systems, sigma q is a bit, but you can recover a non-relativistic limit in this story, and then you get the more usual story where E plus P is m times n, and then you get here the charge to mass, so the density in units of the electron mass that you know usual, and also in this non-relativistic limit, right, you're left with anomalous heat conductivity, but not with an anomalous charge conductivity. But in a relativistic system, you have these relations. And I mentioned earlier, there are these Lifshitz type stories. In relativistic systems, there's one parameter, sigma q. If you also ignore that, there are funny systems where, in fact, all these anomalous coefficients are independent. But let's not. Since we start from a relativistic theory, for us, this will be the starting point.
Okay. What does it mean in a sense? I'm just trying to understand. These are equations I know very well that they're non-relativistic form. And then you need, as you say at the top of the slide, momentum relaxation. So what does it mean? And maybe that's the point of your talk about momentum relaxation in a relativistic theory.
Momentum is still momentum. So of course it picks a frame, right?
Right. So it's just, I just imagine things going fast in a system with impurities. I mean, is that as simple as that?
The impurities tell you a frame, right? The rest frame of the impurities break the Lorentz invariance, and then I can understand.
The level of symmetries, boosts, and spatial translations are 2 independent symmetries.
Say it again.
Boosts and translations, spatial translations are 2 independent symmetries.
Okay.
So you have a reference frame, but you don't have Galilean invariance.
Really?
You don't have Galilean invariance. The energy is not p squared over 2m, even though you have a reference frame. I'm just using, that's what you're saying in experimentalist language, right?
It's just that there's no m. You don't have Galilean invariance. It's something else.
Okay. But when you get it, if at some moment later you are like, what is the non-relativistic version? Try to ask me. With this, you can often quickly understand what. Okay, but like I mentioned, sort of one of the interesting aspects of the strange metal system, magnetotransport. So that's the part that I'm going to concentrate on that throughout this story. But let me first give you, before I go there, give you an example of what this hydrodynamics has yielded us for the cuprate stage metals. There are several examples, and I'm biased, so I'm going to give my own example, but to me, it is very interesting what's going on. Okay, so I gave you this list of strange metal thingies, but actually there's a secret in this linear in T conductivity. We sort of said it already. The interesting part is that it continues down to 0T, but the more interesting part is that as it continues down, it undergoes, right? There's various other scales that it passes in the theory. And the fact that the linear in T resistivity, the linearity in a certain way is not the puzzle. The puzzle is that it doesn't change when the underlying dynamics happens. Because in a normal physics, sort of deeper physics and intuition, is when you hit a relevant scale, in a very big picture physics, you expect the responses to change every time you hit a certain scale. And this, of course, is what happens in ordinary metals, right? The moment you hit the multi-Alpha-Regel scale, the resistivity scale, the moment you hit the Debye scale, the resistivity scale. So this is a very sort of qualitative type idea that you learn from dimensional analysis and various aspects. And so the weird thing is that here you don't see that happen. This, if you look at the experiment, this is probably maybe not even the best experimental picture, but there really seems to be happening nothing when you cross sort of a Debye or a Mott-Joffert-Scale. The slope and the coefficient of the slope look to be completely featureless, right? So how do you understand it? But here is another review paper that tries to make the same point, right? They actually note what you expect, and nevertheless you see a linear NT resistivity. So is there some type of theory that comes out? And so one of the things that we did is we didn't design this, but this was one of the things when we rolled out and we tried to understand cuprate phase metals using holography, is we have some sort of model. It's not a particular linear NT resistivity, but the one thing it does have absolutely is that you don't see any feature change in the DC resistivity as the underlying physics change. What do we mean here by the underlying physics changes is that you go from a Drude-like regime to some bad metallish mid-IR regime, and even a worse type of funny metal regime with some intermediate peaks. So there are two changes of regimes here, and in both cases, right, in between, there's nothing that happens in the resistivity. So at least this is a proof of principle of the model, and I'll explain to you the physics behind it, right, why this happens, right? So this is one of these computations in a black hole. Yeah,
just the difference between the two panels is, so I mean, I see that the horizontal scale is different.
Yeah, I'll tell you in a moment a little bit more. But a preview that for numerics reasons, we cannot have a purely numerical reasons. We could not find a range where we saw these features in one fell swoop, but that had to do with the combination of numerics. And I'll tell you a little bit more. So what we did here is we just took one of these models, we flow it to the IR, but on top of that, we put in an explicit lattice and sort of inspired by the fact that you have ions in a crystal lattice, sometimes called an ionic lattice. There's a periodically oscillating chemical potential that breaks translation invariance in the system. And then when you solve this is now hard because this is now solving new general relativity with explicit spatial dependencies. There's no beautiful symmetries. So you have to do this numerically. And you get very funny things that people would have never thought of in general relativity. You get black holes with a spatially varying horizon size and all kinds of other things. But this is because at sort of infinity, you're holding this fixed, okay? And then you can compute all these things by this dictionary that I told you. So they are just in two different models. Doesn't matter. But let me now explain where this feature comes from. The first to answer Ilya's question, right?
And another question too.
Okay, then I'll ask, but let me first ask your first question, right? So there's a numerical window where we can do this, which is related to the temperature and the size of this lattice that we do. And sort of if we make the lattice very large, the numerics become very hard, or if we make the temperature very low, become very hard. So there's some balance. And that's why we couldn't find a regime that we could have these three regimes at the same time. But by this shift, we strongly believe it is just a feature of the whole thing. If we could resolve this numerically, or we could resolve this numerically, we would see all of them in one model.
So just to make that clear, so these two panels actually should connect to each other. And they're slightly offset in the vertical direction because
I've changed.
Because you've changed.
Yeah.
So connecting to something you said at the beginning, that it's also when you do this ADS-CFT approach, it's good to see that you can recover more conventional things as well. Like you even said that you can get Landau Fermi liquid theory correctly. I mean, very stupidly, if I just have periodic potential, then solid state physics telling me I should get energy bands and all this kind of stuff. Is that something that also can be reproduced? I mean, this kind of very boring solid state physics.
If you would do this in the holographic Landau Fermi liquid regime, I would. It's a good question. I would have to think.
It is not very interesting. It's curiosity.
Yes, I believe so. You'll see a version of energy bands showing up in a moment, but not sort of in the electronic sector, but in a different way. If you understand, Anyway, so the point is you can compute everything here. And one of the things you can do here also, like I said, is you can actually compute, this is not something you can measure, but you can compute the response at imaginary frequencies and imaginary momentum. So you can actually probe the response in the full complex plane. And that is useful. We already saw the talk by Yannis yesterday, right? Because you can really identify what features govern your response, right? If you have a simple Drude response, you would expect a single pole precisely on the negative frequency plane at omega, the size of omega being equal to the relaxation time. So the interesting part is this is a Drude-like regime, but then when we look at it in complex frequencies plane, we see something that is unexpected. There is not a single pole, there are two poles here. And this was a big surprise. At least dynamically, it tells you what's going on in this transition. What happens actually as you increase the temperature, these two poles collide in the same mechanism that Yannis explained yesterday. They can now become propagating modes. So one of them become propagated and pulls the Drude peak, right? It's very soft, but it pulls the Drude peak off zero axis, and that's why this starts looking bad metallic. Okay. So dynamically, we understand what's going on. But like I said, I just have a numerical computer. It falls out. You want to understand what is going on here. So what is the physics that is going on here? And Eric already alluded to it. But remember, the lesson was this: all of this should be hydrodynamics. We certainly know that one of these poles should be hydrodynamics. So can we do better, right? So now this is charge hydrodynamics in this relativistic notation. Relativistic is easy because sort of energy and momentum are in one equation, right? And then if you look at the fluctuations, that's what we're doing. We're doing gentle probes in Peter's language, right? There are three modes that couple. There's the energy mode, there's the charge density mode, and there's the longitudinal momentum mode. So we expect three modes, and one of them is sort of, this is the charge diffusion mode, and then there are two sound modes that couple. This is what you expect to see. As I said, we don't see that, but the key point, of course, that we realized after some time is that we're doing this not in a translationally invariant background, we're doing this in a lattice background. And any sort of dynamical equation in the presence of a lattice, Bloch told us you should not use Fourier modes. You should Bloch waves decompose it. You should enforce the discrete translation symmetry in the system. And that has consequences, which in the condensed matter language is known as umklapp. It means that these waves modes. We saw this also in Janus' thing. You get copies of Brillouin zones in the story. And at the edges of Brillouin zones, these are going to interact. These are your bands that are forming, right, in this system. Right, so this is already, of course, long known, also in the context of hydrodynamics. The interesting novel aspect of this is that we do it in charged hydrodynamics. That, to our extent, to our research, was never done before. Now, it does get very complicated very quickly because without the lattice, we already had three coupled modes. So if you do sort of first order umklapp, first order beyond that, you get 9 modes, right? That's a lot of modes. Fortunately, there is a discrete symmetry in the system that decouples 4 of them from the other 4. So you end up with 4 modes in the system.
That's not better.
This one is not any better, but there's an analog version. Okay, and so what you get is you get a classic umklapp mode, which is a mode that, even though it lives at zero momentum, it's fixed. It's a copy from the first Brillouin zone where it lives at the lattice momentum G. And so now in the low frequency sector, you don't have 3 modes, but you have 4 modes actually in the system. And one of them is this charge diffusion mode, which formally sits at the lattice vector C squared. And this actually is the new mode that you saw here. And for those of you who know different ways of approach, this actually agrees with a completely different approach of doing this. It's called memory matrix technique. And then you see all the things you know from lattice responses. There's at the edge of the Brillouin zone, you have level of repulsion due to the interactions. Interesting enough, this is simply at the edge of the real Brillouin zone, but you also do have this in the imaginary frequency plane. So if you go down, you have the same physics going on. And we can completely understand it now that we have understood that it's sort of this umklapp hydrodynamics or this Bloch wave hydrodynamics. we can actually compare what we get out of our numerical black hole computation with just an ordinary simple hydrodynamic analysis, and it matches to the T. So we really understand what's going on, and it's no longer a black box where we do these computations. And this is now what's going on. This is actually this charge, umklapp charge diffusion mode that just collides with the ordinary Drude mode in the system. And when they collide, then you get a different type of regime what you would see in the AC response. So this collision can be described in an interesting way. And the important in this story is, of course, how this behaves as the temperature in street. So this is rather similar to strange metals. It's a very good Drude-like response at low T, and at high T, you get a more different response, right? And in particular, here's a slightly...
In the top panel, do they have to have the same scattering rate, these balls? I mean, their width that comes out, is that the same?
I'll show you the analytic expression for the width in a second, what goes on. But generically, they... well, I mean, these are very close in imaginary plane, right? So the effective width of both is very same. When they collide, the width is formally the same.
They're formally the same.
Yeah. But at very low T, the charge diffusion mode comes from, right? So if you're very, very low temperature, you only have the Drude mode. Okay. So here's a slightly improved version where you see a little bit better that there's a peak that's moving off the zero frequency axis in the system. And the interesting part is, so this is just the computation, but as I mentioned before, Blaise and collaborators had already found in the data that this slight moving off the peak actually is something that happens in real cuprates at higher T. Now, it would be really presumptuous of me to claim that this is exactly what is going on, right? But at least there is here a phenomenon that describes the same physics that you see in the cuprates. Okay.
Not just cuprates, lots of like oxide metals have this phenomenon.
Yeah. But what you need for this mechanism is some kind of larger periodic structure in the system that would allow this charge. Yes.
So suppose it wasn't, a periodic structure, but just spatial disorder with some characteristic length scale.
Yes.
Could some of this survive? I just replaced G by 1 over the correlation length.
That's a good question. I wouldn't immediately. I would not want to bet left or right. I would hope yes, from this point of view, but my suspicion is no. Okay. However, I have not answered the real question that I started the motivation with, right? The real question why we started to understand is why doesn't the resistivity scaling with temperature change as I change these going from one regime to the other? So one of the things that this umklapp hydrodynamics allows us to do is it allows us to compute exactly what the resistivity is in this story. So let me express it in terms of the conductivity. And so the first thing you see is that when you write it in a certain way, that it is actually determined by 2 timescales. So your intuition that when one timescale starts taking over from the other, this should change is right there in the formula. So why do I still not see any time change here? Well, the reason here is that actually it's because we started from this sort of SYK ADS2 time point. And that actually means that these 2 expressions, which are complicated expressions of this, let's call it sigma q, or the incoherent part of the conductivity, and this object has the viscosity in it, right? If you compute these in this model, these transport coefficients are fixed by the scaling of the underlying quantum critical point. And then if you compute these 2, they happen to scale exactly the same way with temperature. And it's the fact that you started this from a quantum critical theory. So it's not the umklapp hydrodynamics, but it's the fact that you start from a quantum critical theory that tells you that these 2 naively independent scaling rates actually secretly scale the same. And that's why you don't see a change when you go through the from one regime to the other. Okay, so one thing, a very quick answer to some of the more high energy theory. So I put in a lattice, right? So lots of people who do computations on quantum Monte Carlo, and they put in a lattice as a regulator. The whole point is that the lattice is irrelevant in the RG flow sense. So why do I get features now that where this lattice is so firmly imprinted, right? And the reason has to do with the scale at which I chose this lattice vector. Right? If I make the lattice very, very small, indeed everything that I see just flows away, and there's nothing remnant of this lattice in the story. The reason that what did happen is that the collectivization or the hydrodynamization of this theory happened before it started to realize that there was a lattice. So I have a liquid flowing in a lattice rather than an object that becomes can collectivize and scales larger than the lattice scale. So this is this sort of same comparison that I had earlier. It's the relevant scales and problem. And you can do this. You can do exactly the same phenomenon where you take a very short lattice, and then indeed nothing of this interesting physics happens. So it's important that the lattice is sort of a super large scale compared to the onset of hydrodynamics. Otherwise, you will not see these features. Okay? Now it's very easy for me to explain the next feature, right? Remember, there were not 2 poles, but 4 poles. So if I just enlarge my window, I get the sound poles as well. And this next regime change is when these modes that are now propagating are starting to interfere with the sound modes in the system. And then you get the sort of really fully incoherent regime in the story. Okay, so this was a motivation, right? This is just one example of what hydrodynamics or what you learn from holography and hydrodynamics sort of can teach you some things about strongly correlated systems in return. But now let's go to what I already advertised. Let's try to understand the magnetotransport or the whole transport in the system, partly because this is such an important part of the strange metal phenomenology. How am I doing on time? Okay. All right. So let me go rather quickly. So based on this sort of insight that you get from relativistic systems, there was already an early idea by Blake and Donos how you might explain the whole angle phenomenology in the system. The point is that the best way to understand this sigma q is the part of the conductivity that has no overlap with the momentum current in the system. And in particular, that means that sort of in the longitudinal conductivity, right, it's sort of, you can think of it as particle creation, or you have 2 particles with equal densities, right, then there's no net momentum in the system. So they contribute no net momentum, but they do contribute charge. But if you do these type of systems in a Hall response, they will feel, even though the origin of it has no overlap momentum current because of the bending in the magnetic field, then it will be sensitive to the momentum current, right? So the idea some way or another is that the Drude part, or the part that feels momentum relaxation, sits in the Hall current because that's unavoidable. And then some way or another, the longitudinal response is sort of this overlap without momentum. And then sort of you can decouple the momentum relaxation scale because that only sits in the Hall sector from the longitudinal scale. Now the puzzle, right, is this, that is the fact that in many metals and in strange metals, you see a very Drude peak. And Blaise is actually one of the ones who has advocated this very strongly for many years, is that in real strange metals, you see a very strong Drude peak in the longitudinal resistivity. And the normal way we understand the Drude peak is that is the momentum relaxation. This scenario that the part of the conductivity that does not overlap the momentum tells you what the longitudinal response is very hard to sustain in the presence of an observed Drude response in the metals. Okay? So now I need to go a little bit quicker. So there are these features in magnetotransport and cuprates, but there are other interesting, more subtle features in the cuprates as well in magnetotransport. So one of the things is that if you look at the cyclotron mass and as a function of doping, this is actually one of Peter's experiments, right? You see that it changes as a function of doping. This is very weird, right? Normally, the cyclotron mass is just related to the charge to mass ratio in the system that you don't expect to change, even if the mass itself has been normalized. It's just whatever it is. But now it changes with doping. This is very puzzling. And one of the other things, and this is more sort of people measure the whole response in the system, and then from the whole response, they often deduce the effective density in the system, right? This is a very simple Fermi liquid type calculation, but you may wonder whether this is true in a strongly interacting system, right? So here you see actual measurements of the whole response, but it's even the axis tells you it's this NH rather than simply RH, which is what one of RH is. So we did, in a long story short, we did the same sort of umklapp hydrodynamics and also numerical relativity story now in the presence of a magnetic field as well. And there are several interesting things that you find is indeed, actually, you get an anomalous cyclotron frequency. You no longer get a very simple relation between the charge to mass ratio. And that's essentially because there are cross correlations due to the lattice in this susceptibility. You can think of the cyclotron frequency as a ratio of susceptibilities rather than a simple quantum number relation. But the curious part is that even though these objects changed, whereas rho hy formally is sort of the cyclotron frequency and the plasma frequency squared, right? That this actually stayed to first order. And there are some details here, so right, you can compute all these things in this umklapp hydrodynamics to large order, right? And actually, it turned out there was a large cross correlation with people who also looked at hydrodynamics in translational symmetry breaking, but specifically charge density wave hydrodynamics. So there was another order parameter in the field, but the order parameter is not necessary to understand it. There are these very interesting coefficients that appear, and you can compute everything to restore. And then there's this curious object that, if you look at the whole coefficient in this zoning, this is what you compute analytically, and you have this top layer divided by this bottom layer. So if this lambda is small, you get a very interesting further order cancellation in this system, which allows you to understand. But anyway, you can, as I said, you can compute these objects to your heart's extent. Peter, we were talking, these are where these higher order susceptibilities come in. And again, you can test sort of your hydrodynamic theory versus your numerical black hole computation. Everything matches to the story. So can we say something new about the cuprates? What about the whole angle scaling relativity? Well, the one thing that comes out here is that as long as your lattice is still relatively weak, right? You see, this is the longitudinal resistivity, this is the whole angle resistivity. So if you look at large temperature, they are essentially the same. Only here at low temperatures, at very, very, very large lattice strength, do I start seeing a deviation of the cotangent of the whole angle from the longitudinal resistivity in the system. And the underlying physics of this should be very clear. So even though we have all these new novel effects, right, this is still simply the fact that when you have weak momentum relaxation, there's a longest time scale in the problem that sets both the whole response and the longitudinal response. So that's the story. In essence, this is nothing more than the Drude model recovered. There was a hope you could see something new. And like I said, we do see many, many new things, but this particular question stays as it is before. Okay. So you have to consider some kind of, and this is the motivation for the title of my talk. Right? This has led us to think, okay, if weak translational symmetry breaking with all these new features cannot explain it, even though it does so well in other things, we are basically now forced, as long as you're staying in a single fluid type model, right, which is at its core sort of an isotropic type fluid, you have to now consider strong translational symmetry breaking. And this was the motivation. So this was my personal motivation. There are other people who are thinking the same way. So this is a famous result from 2020s on the longitudinal magnetoresistance. And what people found based on earlier work by Analytis, which was not in the cuprates, but was in other strongly correlated systems, that the longitudinal resistivity has this funny square root type behavior as a function of T and B, right? And this non-analytic square root you can actually understand if you assume that, Eric already showed it, that instead of having sort of a homogeneous system, you have systems where the resistivity is one type and the system another type. This is called effective medium theory. But you can clearly see that translational symmetry is strongly broken in these types of systems. And this is what allows you to get these funny square root type behaviors. So at the time I was actually talking to Nigel Hussey a lot, and I was very biased that you could never get this if you understood sort of in a hydrodynamic type response theory. There's no way you could ever get a square root if you take hydrodynamics with sort of small corrections to it. But if you allow for strong corrections or strong translational symmetry breaking, then you. And then there's there's another feature. This is actually an STM of the superconducting condensate in the overdoped region of Abisko, and you actually see a large amount of disorder in the system. And this has now been sort of used to explain not the whole strange metallic region, but this particular corner, this foot of this strange metallic region. So these are other indications that you should really think about strong disorder, strong translational symmetry breaking, in this particular case, disorder in these systems, okay? So that's what we set out to do well. I only need a couple more minutes.
You have 3.
I have 3. So to do that in these systems, like I said, numerically, they're very heavy. So we first did a simplification, right? So what does strong translational symmetry breaking, if you start from this type of model, we didn't do disorder yet, let's stick with a periodic lattice, that's numerically easy. That means that this ratio is very large. The easiest way to get this ratio very large is you simply set mu to 0 rather than delta mu large, right? So this is, okay, this is a simplification, you lose a scale, you get scaling collapse. And as Eric already said, there are actually examples of people who studied graphene at charge neutrality in these systems where you have an underlying corrugated substrate. This was also partially inspired by this, or inspiration for this paper by Andy Lucas and collaborators, right? And so I won't go through all the detail, but one of the main things that you see is that in 1D, you get this very anomalous response. Since there's no conductivity, you don't expect a Drude peak. But I can now very easily explain in terms of these poles what's going on is that it turns out that it's sort of these sound-like poles in terms of Umklapp hydrodynamics that dominate the charge response, and the heat response is precisely the other 2 of these 4 modes. It's very funny, right? Sort of 2 modes out of 4 modes down determine the heat transport, and the other 2 determine the charge transport. If you put in a tiny bit of mu back, then you see all 4 of them again. Right? But in this regime where mu is very, very small, of course, there's now a balance, like Eric said, in the weights of the system. The most interesting part is what happens in 2D, where we did see, even though right, there's no Drude pole in the system, there is some kind of Drudish-like response in the system. And as Eric explained the last time, the reason you can understand this is because you have this funny flow that now flows around the various obstacles. This is also some sort of effective medium type picture where you have systems, right, which have low resistivity and systems which have high resistivity in the system and the translational symmetry breaking. So this feels very effective medium-like, right? Now we have 0 mu, so we cannot text the whole response, but you can try to sort of see if you get sort of this non-saturating longitudinal magnetic resistance. This also rolls out. I refer to Eric Nielsen's talk. And then to clean up. So this is a very nice, interesting. This has a Drude-like response with a non-saturating linear longitudinal magnetic resistance. This is not a strange metal, right? It doesn't have any of this SYK type features because SYK needs this finite mu. So what we're doing right now is we're reintroducing a small finite mu because I need strong translational symmetry breaking. And then one of the things you can see is that at least, right, all this longitudinal, sort of this linear in B at large T, non-saturating longitudinal resistance stays. This is preliminary results. And at the same time, because I have a mu, my Drude response actually increases. So I have a system here which starts to have features of a strange metal that we hope up, and where, well, this is preliminary. It's a teaser for what's coming up with Eric. So, and I'm happy to discuss it further. But with this, I want to thank you very much for your time, and I'll leave this slide. Thank you so much.
Yeah, thanks a lot, Koenraad, really beautiful talk. So you motivated your periodic potential just, naturally by saying we have a lattice in solid state systems. But, in like the cuprates, I guess there's lots of evidence for, many competing short range ordered, states, stripes, charge density waves, and so on. Could I think about this as maybe also being related to some, fluctuating order parameter, actually? I mean, this is static, but I don't know how you would even treat that problem. But if I imagined, coupling my ADS CFT thing to some kind of fluctuating order parameter that had spatial structure like this, is that
So I would ask, do you mean really a dynamically fluctuating or just a randomly disordered? So as you know, there are these, that's also referring to right here. So these type of studies, and there's another study here.
Yeah.
Right, they study systems where you don't have a homogeneous order parameter in the system. Right. But you do have static, but you have patches where the order parameter, for instance, this has a nil order parameter, but the orientation is different in different patches. So that's also strong in that translational symmetry breaking, right? So those type of models start to look very SYK-like, and so and then they induce sort of these secondary effects there. But
but that's probably hard.
But that's not a dynamically fluctuating. So it's not a.
See, but I guess either one of those would be challenging to incorporate into the framework you guys are.
If the moment it's disordered, it's hard, right? If you want me to make a square lattice of a nil order parameter that changes locations, that probably
You could do.
So let's see, two questions. One, how does this picture of the importance of disorder kind of fit into things that, for instance, people like Patel and Sachdev have been pushing in terms of disordered couplings as being a kind of essential physics of the strange metal story? The distorted local couplings. Second, do we get any insight at all from this? So it's a very beautiful picture and very impressive. Do we get any insight at all as to why some metals are strange and some metals aren't?
For the latter one, I would say at this moment, no. For the first one, there are two types of disorder in these Yukawa or these SYK type models. There's sort of this intrinsic disordered coupling that Peter also asked for, that sort of happens in abstract end space. That's not the disorder that I'm talking about here. This Yukawa SYK model, the one that reproduces 5 of the 6 of the features that you see in the strange metal, it also has spatial disorder, and that's the disorder that we're talking about here. They're somewhat related, but they're to most extent they're independent. Ilya actually knows it better than I do. So there are two types of disorder in these models, and it's the spatial disorder that's important. Not the other. The other is a trick to solve it.
So I'm trying to understand your answer. As I understand it, in those kinds of models, people speak of potential disorder, which is kind of the normal disorder we think about, and then there's disorder in, like, say, the J's,
yes.
Some local couplings, and those are kind of essential for that. So,
yes. but there's also a local component to that, and that's important.
Peter, is there a propagating mode? If you look at what these poles do as a function of K, do they move?
And I've only showed you.
This was all Q equals 0, basically, right? Did I miss the slide?
Yeah, but the answer is yes. So we can do it at finite Q as well, but there are propagating modes as well.
They propagate diffusively?
Depends. The point is you now have so many extra modes that some of them
are
and some won't.
Holistic.
You cannot propagate diffusively.
Well,
Propagating means the real part. Diffusively means the imaginary
okay.
part.
You can propagate diffuse. If I put milk in my coffee, it spreads. So that's whatever that is. This does that, right?
So I mean, these are sound modes at the Umklapp wave vector, right? So you would say these are not propagating because I said that k is 0, but it's obvious that when I start increasing k, right, sort of these start to move. Same with these ones, right?
And this Q equals 0 system is degenerate, right? So as you go away from Q, you will get
Actually,
more.
this parity, odd parity, even also relies on Q.
So you get 9 of them.
So the moment you have finite k, you have 9 of these modes. They're all over the place. Some of them are purely diffusive, some are propagating.
I hope it's not too far removed, but I was really intrigued by this point that you can recover, Landau Fermi liquid. I mean, if you can do that, then maybe you could address, Peter's question. If I then push the system more into a Fermi liquid regime, see how all of the story changes, and try to interpolate kind of between the strange metal and Fermi liquid. Is that very challenging technically? I mean, do you have to do complicated things to get the Fermi liquid to begin with? I guess the whole point of this approach is that you can, you want to deal with the strongly correlated regime, but if you can see how you go between strong and weak correlations, maybe that could be education.
I can think about it.
Okay.
So I'm not sure what you meant by holographic Landau Fermi liquid. But there's no regime where we have quasar particles in holography, right? In any of these black holes.
Yeah, so the puzzle is that you get Blaise is referring to is you get a system which has a standard single fermions that form a Fermi liquid, but there's always other stuff as well. So when you compute the response of the system, it computes the response of everything, not just of this Fermi liquid. So you would have to do some extra machinery to disentangle only the Fermi liquid part from the other part.
I see. So it's probably too naive to think you can go between T squared and T, like resistivity, for example. It's kind of...
But it's something to.
I think we will thank Koenraad here once again.